So let's talk about the null hypotheses here. So now what we're going to do is find the differences first, then get the mean of those differences. And we're saying if they are indeed not that different from each other, that mean difference should be 0. The alternative is that the mean difference is not equal to 0. Once again, alpha equals 0.05, two-tailed. And now we will draw our S dot bar, which means the S dot, it's a standard sampling distribution of mean made of differences, right? Okay, so here, we want to put 0 here. We probably also want to figure out standard error somewhere along the line, which is going to be S sub d bar, which is S sub d divided by square root of n sub d, right? And we probably also want to find the degrees of freedom, which is going to be n sub d minus 1. And we probably also want to find the critical t. So let's find all that. So here I'll start my paired sample section. So I'll also start with step 3. Let me move all of this. Let me move this over here. We're going to have to change this. Excuse me. All right. So let's start here with step 3. Let's find standard error, and that's going to be S sub d, not d bar, divided by square root of n sub d. Right? And so we can find S sub d very easily, and we could also find n sub d. So S sub d is, actually, we need to first create a column of d's, right? I was going to find the standard deviation of the d's, but I realized I don't have any d's. Let me just make all of this a little bit smaller. So the d's look something like this. Silence minus background noise. So this is how many more words they're able to hear accurately in silence than in background noise. And here we see that some people hear a lot of words better in silence. Some people hear words better with a little bit of background noise. Some people are exactly the same, right? So it's a little bit mixed. So we could find the standard deviation of all these differences. And we could also find the mean of them. And the mean of, the n of them. And the n of them will be the same as 24 because there's 24 people that it came from. So there's 24 differences. Now we could find out standard error. So standard deviation of d's divided by the square root of 24. All right. So that's standard error. Notice that it's quite different from finding a standard error of independent samples. Now let's find degrees of freedom. Degrees of freedom for d. And that's going to be n sub d minus 1. And that's 24 minus 1. And so our critical t, I'm trying to keep it lined up, right? Our critical t should be t inverse 0.05, two-tailed, 23. Put this as a pointer, 23. And we get 2.07. So far it seems that our critical t, our standard for how extreme it has to be is more far out. And that makes sense because our degrees of freedom is smaller than 46. Okay, so it's plus or minus 2.07. So plus or minus 2.07. Now let's talk about our sample. In order to find our sample t, we want to find the average difference, subtract from it mu, the hypothesized mu, and divide all of that by standard error to find out how many standard errors away our sample mean difference is. And then we also want to find p-value. Okay, so here's step 4. Our sample t would be d bar minus mu divided by standard error. So what is d bar? And how would we find it? We would just use the average function, find the average of our d's, that gives us d bar. And now we could do d bar minus 0, same thing, over standard deviation, standard error, right? And what do we get? 2.97. Why, what do you know? That is more extreme than 2.06. Let's figure out why. Well, first we might look at whether, so look at this standard error. So this standard error is much smaller, right? And it's saying the steps are smaller, right? So how many steps we need to take to get all the way out to this d bar? There's more of them than these bigger steps. These are almost twice as big, right? So these bigger steps, there's fewer of them that you need, right? And that's what the sample t idea is. It's how many of these standard errors, how many of these steps does it take to get all the way out to d bar, or x bar minus y bar? And we need almost 3 steps out. And so what is our p-value? Our p-value should be less than 0.05. So that's going to be t dist. Here is our t-value. I'll put in our degrees of freedom and two-tailed. And it's 0.007, right? And that's certainly less than 0.05. So in step 5 here, we reject, whereas here we failed to reject. So since there is this difference, and we detected it with this one, but not with this one, we would say that this is a more sensitive test, given that there is something to detect out there, right? So this one can detect a difference if it does exist. This one is a little bit coarser. There's a couple of reasons for that. One of the reasons is because of standard error. These standard errors are usually larger than this standard error of differences. Another issue is that x bar minus y bar, the difference here was, so if we look at x bar, minus y bar, this difference is roughly around the same, I think. Yeah, this difference is the same as this difference. So it's not that, but it's that you're dividing by a smaller standard error here than you are here. Here, the standard error is quite large. The steps are quite large. Here, the standard error is quite small. The steps are quite small. And it's because you're taking out some of the variation caused by having some people just being able to hear a lot of words accurately all the time, with noise, without noise. And some people aren't very good at hearing anyway, right? So they might have overall low number of scores. But with D-bar, you don't care about those individual differences. You end up accounting for those by subtracting them out. And so here, this is a more sensitive test. So here, we get P equals 0.0067, was it? Something like that. And we reject the null. Yay! So which test is more sensitive? Which test is able to detect a difference if there is a difference? Paired samples, right? So that's why paired samples, it's a little more complicated to actually collect that data, but once you do, it's actually worth it because it's a more sensitive test.